So today we are going to take off from where we left off last time. In the last time's video, we wrote down this relationship. This tells us where the mass of a mass spring system is at any time t, given the amplitude of oscillation, given the angular velocity, and given the phase constant. Remember, the phase constant tells us how the oscillation started. Where did we start the timer? Where was the mass when we started the timer? It's important to understand the phase constant. So what I'd like you to do in your own time is to look at page 382. Read that section and also look at your workbook, because there's some practice examples in the workbook that really help you nail down the meaning of the phase constant. What we're going to do today is to consider that, well, this tells us the position at any time of the mass spring system, but we also want to know what its velocity is and what its acceleration is. So we left off last time talking about where physically we think the velocity should be for a mass spring system. So imagine if there was a mass on this and it was going up and down like this, then where is the velocity 0? Well, the velocity is 0 at the end points, the turning points, that is at x equals plus and minus a. And if you think about it, I hope you can see that the velocity is a maximum when the mass is passing through its equilibrium position. So we need the physical understanding first, but mathematically, if you know your calculus, it's actually pretty straightforward to obtain an expression for the velocity. So see if you can apply what you know of calculus to come to this conclusion. The expression for the velocity is what we've written down here using the chain rule. And what that's telling us is that just as a here is the maximum value x can have, all right, so remember, if we want to know what x max is, then the maximum value cosines and sines can have is 1, and therefore the maximum value of x is a. Similarly, this tells us that the maximum value of v is omega times the amplitude. Now, where did this come from? It came from the fact that v is nothing but dx by dt. But you also know that the acceleration is the first derivative of the velocity. So if we do the derivative one more time over here, this is what we'll get. So again, using the same logic we did before, this constant that multiplies the trig function is the maximum value of the quantity that's on the left-hand side. So this is actually a max. So we've actually learned quite a bit here, but make sure you understand it physically. Make sure you understand where you think the acceleration should be maximum. Remember, acceleration is rate of change of velocity. So wherever the velocity is changing the most dramatically, that's where acceleration will be maximum. And thinking about it, I hope you can see that that is the case at the turning points x equals plus and minus a. Another thing you can do to make your understanding more concrete is to draw a graph and remember the following. So let's draw a couple of quick graphs to remind you, and I'll let you work on this in more detail. So this is x, the position of the oscillator as a function of time. And again, to relate it to the physical system, let's remind ourselves what we're talking about. We're talking about either a vertical or a horizontal mass spring oscillator. So this is the vertical example. This is the horizontal example. And in either case, we're assuming no friction and no air resistance. In either case, the x-axis here is this way, the x-axis here is this way. So x describes where the mass is located. So let's say that for a particular value of the phase constant, the oscillation looks like this. Okay, and this is clearly not accurate because it should be symmetrical. But you can see that this is what is called a sinusoidal function, a function that is sine or cosine or some kind of combination. And what you should remember from physics 1 is that a velocity versus time graph of this oscillation is essentially going to be one where you take the slope of this graph and then draw the slope over here. And I'm going to leave it as an exercise for you to try to figure out what is the appropriate velocity versus time graph for this x versus t graph. Remembering the following: slope here is 0, slope there is 0, slope here is maximum, and slope there is maximum. And then slope this way is negative, slope that way is positive. So see if you can reconstruct the velocity versus time graph here. If this is not easy to do immediately, what you might do is start with an x graph, x versus t graph that's pure sinusoidal, like either pure sine or pure cosine, and then see if you can figure out the corresponding v versus t graph. Now, if I had asked you instead to draw an a versus t graph, the acceleration, how does the acceleration change while the mass is oscillating? Then it's actually easier than you might think, because if you look at these two equations, look at the x equation over here, look at the a equation over here, notice that they're both cosine functions. The only thing that's different is the constant. Okay, so there's going to be some a max here and a minus a max here, and then there's a minus sign relative to the x equation and the a equation. That tells us that the graph for acceleration versus time is simply a mirror image of the graph of x versus time. So all we have to do is to flip this graph so that it would look something like this, like that, and so on. So going from x versus t to a versus t is actually easier than going from x versus t to v versus t. So if you practice this from the video, from the textbook, and from the workbook, then you should be able to go easily from one kind of graph to another, and you should also be able to understand the meaning of the phase constant. So we are going to briefly talk about energy in simple harmonic motion, and I'm going to remind you of a few things, and then we'll stop. And then what I'd like you to do is to use the worksheets, the self-test packets that I'll be giving out to you in order to complete your understanding of this material. So let's go back to this part of the whiteboard, and we're going to talk a little bit about energy in simple harmonic motion. So again, we are assuming no friction, no air resistance. So we expect that mechanical energy is conserved. Okay, since force of friction is assumed to be 0, and by friction I also mean air resistance, dissipative forces. So a few things to remind you about: that for a mass spring system, imagine a horizontal oscillator like this, where this is the equilibrium point at x equals 0, and the oscillator is going from minus a to plus a. So it's going back and forth. Well, if mechanical energy is conserved, that means that this quantity k plus u of the spring, must not change. The total quantity must remain constant, even if k changes and u changes. And to remind you, the kinetic energy is of course half mv squared, and the potential energy stored in a spring, you should remember from physics 1, is half k x squared, where I'm going to make a note about the x here, the x is not the position, but it's the displacement from equilibrium. So in other words, we should strictly speaking write us equals half k delta x squared, where delta x is the position minus the equilibrium point. But since we've set this equal to 0, we have chosen the equilibrium point to be at the origin. Essentially, delta x is the same as x. So it's important to recognize that this is measured from the equilibrium point, because there might be some problems and some situations where the equilibrium position is not at the origin. So it's important to remember what that means. So if this is a constant, well then let's look at how energy is changing form as the oscillator goes back and forth. So you know that the oscillator stops here for a moment before it turns around, which means at this point there's no kinetic energy. All the mechanical energy is in the form of potential energy. Again, that analysis is true of this position, x equals minus a, where the mass is about to turn, so it stops for a moment. So I hope you can see that it's at the equilibrium point, when the mass is passing through the equilibrium point, that it has no potential energy because the spring is stretched to its natural length. It's not storing any energy in compression or extension. So all the energy is kinetic here. So since all the energy is in the form of kinetic energy at the position of the origin, when the oscillator is passing through equilibrium, this is also the point at which the velocity of the oscillator is a maximum. So there are a number of statements we can make following from energy conservation of the oscillator, and I'm going to quickly write them down over here. So we just wrote the general form, the general expression for mechanical energy, which is this. This is true any point along the motion. This is always true, that this thing is a constant. Okay, but we also said that the mechanical energy at the extreme positions is all potential. So that's half k, at the extreme positions x is equal to a, so it's going to be this. And since the total energy doesn't change, this is a valid expression for the total energy as well. Similarly, this is also true, that E mechanical is half m v max squared. Now this is true at the origin, but again, because energy is conserved, it's also true everywhere. So you want to understand that these three statements are true statements about the mass spring oscillator, vertical or horizontal, in the absence of dissipative forces like friction and air resistance. So if you think about it, there's a logical step that follows. If Emec is this, and Emec is this, and Emec is this, then it's logical to say, well, this must be equal to that. And when we do that, and I'm not going to do the full derivation here, but you can look at page 385, look through the derivation at page 385, where we equate half Ka squared with half m Vmax squared. And doing so yields a really interesting result. And I'm going to write down just the final result, and I want you to see if you can work through that little derivation at the top of page 385. So here's the final result. If we realize that these two energies are equal, because energy is conserved, we equate them, then the final result gives us information about the period of oscillation. In other words, the time taken for one complete cycle of oscillation. So the equation that we get looks like this. This is the final equation from going through this analysis to its logical point. What does this tell us? This is an equation about the period of oscillation of a mass spring system, vertical or horizontal. To remind you, the period is as follows. If this is minus a and somewhere here is plus a, the period is the time taken for one complete cycle. So let's say you're counting from plus a to go from here and then to minus a, and then back to plus a. That's one cycle. So t is the time for that, and it tells us that the time for one complete oscillation is proportional to the square root of the mass spring system, and inversely proportional to the square root of the spring constant of the spring. And we can relate this to a number of everyday phenomena, which we will do when we meet face to face. But for now, if you can understand physically how energy transforms during simple harmonic motion in the absence of friction and air resistance, and how it's conserved, and how energy conservation yields this result about the period of an oscillator, then that is a good point. That is a good thing to have done before we meet face to face. So I'll see you in class.